doing a little variation on the problem, the SMO Junior 2007 problem 35. I think the problem they asked was find the smallest case such that this condition holds. I'm looking for the number of integers case such that k plus 1226 and k plus 666 are perfect squares. Now, we effectively just force the condition to happen with these two statements right here. In other words, we force k plus 666 equal a perfect square, and also the same with k plus 1226. You see just right here, these conditions literally force impose the condition we're seeking. Now, notice that if we subtract a squared from b squared, we actually just get this constant 560. And we're also fortunate enough to have a little bit of algebraic structure here. The difference of two squares, b squared minus a squared, is the same as b plus a times b minus a. So you have two binomial factors equal to 560. Now, 560 is actually equal to 2 to the 4th. And this is something that could be done. I'm just going to write down the result, but it's equal to 2 to the 4th times 5. Oops, I lost my marker. Okay, 2 to the 4th times 5 times 7, right? Now this is important. That's supposed to be, okay, y'all, that's supposed to be 2 to the 4th times 5 times 7. And I'm going to put a 5 to the first power and a 7 to the first power right there. And again, this is supposed to be multiplication right here. Okay, we're multiplying these numbers together. Okay, it's hard for me to make that mark work. But y'all, what this means, if you take this exponent, this is another kind of number theoretic result. You're going to have 5. You add 1 to 4. And the proof's not too hard on that. 5 times 2 is equal to 20 divisors. Okay, and that's just a nice result from the prime factorization. So we have 20 divisors of 560. 20 divisors, 20 factors. All right, so what you'll notice right here that 1 in 560 is kind of the trivial factorization. 1 times 560 is 560, but notice what happens right here. It creates a system of equations. And notice that if you add the left-hand side to the right-hand side, the a's cancel, and you get 2b is equal to 561. All right, 2b, 560, and 1 is 561. The b's, b plus b, and then but a minus a cancel. But what this means is that b is not an integer, okay? B is equal to something that's not an integer. It's equal to, certainly could say that's equal to 561 over 2. So you see, we're not interested in that. We're looking for integer solutions to this, of course. So this is something that we can't consider. However, when we look at the next pair of factors, here, you know, you just put a 2 here and divide by 2 here, and you get 2 times 280. Notice that we get something that works out. We get 2b is equal to 282. All right, and 2 divided by 282 is 141, right? So that's your b coordinate. And then you can find out easily what a is just by right here. You could, if you do the arithmetic on this, folks, and I'll just write down that you come right up here and you do 141 squared, right? And then that means you can solve 141 squared. Is that a 1? Yeah, 141 squared minus 1226 would be equal to k. All right, and I did the arithmetic for you right down here. And also, it would give you this minus 139 also. I mean, you would find k, then you could come over and find out what a was. All right, which is minus 139, and also you can directly find it right here. If you put b is equal to 141 right there, you need a minus 139 right here to give you 2, right? So that's how you find everything is in place. Now notice it wasn't even necessary to find that k is equal to 18,655. All right, we just know that this has a solution, and so that's going to be an instance of where the K, I just did for the sake of completeness, you found K, but the minute you write down this ordered pair, you know that you can find K, right? So you know that would constitute a solution to this. That would be one of the integers where this would work. Now, I won't go through all of this with you, but we have this one checks off, this one checks off, check off, right? So far we have 3 Ks, right? We have 3 Ks that get the job done. Now down here, for similar reasons on these divisors 16 and 15, you get 2b is equal to 51. So this, we don't get an integer out of this. We don't get an integer out of this. We don't get an integer out of this. All right, now notice that there's supposed to be 20 divisors. On this page that I have here, we have 2, 4, 6, 8, 10, 12, 14. Now there's 6 more divisors on the next page. So let me clear this out. We'll just do that. But so far we have 3 solutions, 1, 2, 3 Ks that get the job done. Okay, now let's clear and let's go to the next page. Okay, so just to quickly summarize, there's 20 divisors. All right, we've done 2, 4, 6, 8, 10, 12, 14 of those divisors. There will be 6 more divisors on the next page. Okay, now notice all three of these divisors led to solutions, and the smallest one, which was kind of like the original problem, turned out to be minus 650. And we can actually remember, keep the minus 650 in mind, and we'll go back to the next. We'll actually see that leads to a solution. But anyway, the answer to this is that there are 6. The answer to the question is that there are 6 K that satisfy the condition. Okay, so there's 6 Ks, if you want to make that an apostrophe S. Okay, there are 6 Ks that satisfy the initial condition. So this is the answer to the question that was asked. There are 6 of them. 6 times it happens. Now listen, the smallest one happens to be minus 650. Okay, so let's go to the previous page here and check that out. So again, minus 650. Now notice right here, you can almost see it if you put, and I'll just go ahead and write it out. For K equals to minus, for K is equal to minus 650, you can see right here, for K equals to, trying to keep it close, K equals to minus 650. And this is essentially the question that was asked on the Math Olympiad. It says, what's the smallest K that gets the job done? So K is equal to minus 650. Now notice right here, if you substitute minus 650 right here, you would get, do I have room here? You would get 576. Okay, you get 576, but that's equal to 24 squared, folks. Whoops. I lost my marker here. This thing, I got to invest in something better than this, ladies and gentlemen. Okay, so 576 is what you get right here, folks. If you put minus 650 right there, you get 576, but that's 24 squared, okay? That's equal to 24 squared. Okay, so that's a perfect square. And then you can see over here, if you put minus 650 right here, you get minus 650 right there, you get 16, right? So you get 4 squared. So you see, you kind of trust the process when you actually see it working. Now for these larger numbers, it's more of a headache. 4 squared is equal to 16. And again, hopefully that's legible, ladies and gentlemen. For K is equal to minus 650, we get 24 squared is equal to 576 right here. And then if you put minus 650 right here, you get 16, which is equal to 4 squared. So this is kind of the problem that's, I don't know, maybe the most interesting problem, but we actually counted the total number of solutions. So as far as the answer to the question, we had 6 Ks that satisfied the conditions. And again, I know I'm sounding like a broken record right here, but Once you get to this stage right here, there's no reason to even to find the K. That's not even a requirement. If you get to this stage where you get an ordered pair AB, you know that the K does exist. And if it's just a counting problem, you're just counting the number of K. So again, this is there are 6 Ks meeting that meet this particular criteria. All right, thanks.